So this video will be the first part of 6.3, Defense Against Infectious Disease. The understandings, applications, and skills that we will go through will be related to that of the immune system. So, with the immune system now is what protects the body against foreign invaders. The immune system uses both physical and chemical mechanisms to protect the body. The physical structures include things like cilia, which can help sweep bacteria away and out of organs such as your lungs, mucus, which can help trap that bacteria, and skin, which acts as like a physical blockade. Chemical mechanisms include the action of phagocytosis, which is really endocytosis, the production of antibodies through recognition of antigens, and the inflammatory response, which is part of the generation of antibodies. So the immune system can be broken down into two parts. There is what's called the innate response and the acquired response. The innate response is really non-specific defenses. So this is kind of a general response that your body will have to any type of invading pathogen. So the innate system will involve things like the skin, the mucous membranes, and chemicals. The second line of defense in the innate system is like through phagocytosis, the use of inflammation, and fever. And then the acquired response is really specific defenses. So these are things geared specifically towards the invading pathogen. So of relevance to us will be generation of antibodies. Those antibodies will be specifically made for that invading pathogen. So within innate immunity, there are two types of innate immunity. There is what we can call the first line of defense, which include the external defenses. These are things like the skin, the mucous membranes, and chemical secretions, which we'll cover in the upcoming slides. And then there are the second line of defenses, which are the internal defenses. Should this first line of defense be breached, then the second line of defense would come into play. And these include things like phagocytic cells, such as macrophages and neutrophils, natural killer cells, which we won't cover in any more detail, antimicrobial proteins, inflammation, and fever. So in the first line of defense, there is that external layer. So the first line of defense against any infection is really the skin. Unless broken, the skin will form an almost impenetrable barrier against bacteria and other pathogens. So many bacteria and other pathogens, viruses for example, do have to enter through the mouth, nose, and eyes, which are equipped with their own special defenses. And so just very quickly, what makes the skin part of an effective barrier is the layers that it is made up of. So overall, the skin is made up of several layers, which includes the epidermis, dermis, and then there's a layer of subcutaneous fat. The epidermis itself is made up of many different layers as well, which is kind of interesting in itself. So at the very top is what is called the stratum corneum, which is basically layers of dead cells or dead keratinocytes. And these are dead cells that have been keratinized, they've had their nucleus removed, so they don't allow things to get in, and should anything get in one of these cells, it shouldn't cause an infection. And so it forms a very nice barrier. And this is the layer of skin that's always being flaked off, or when you shed skin cells, this is what flakes off. And then below this are layers of cells that are always kind of continuously moving up as these layer of dead keratinocytes get sloughed off. So it's always pushing things out, which helps keep things out of the body. Body also will produce mucus, which will help trap bacteria. So there are also enzymes within mucus that can also help destroy bacterial cells. So that mucus that is produced in response to a respiratory infection is helping to trap that bacteria or trap that pathogen, and then help you expel that mucus when you sneeze or when you cough. Now, lining some of our organ systems, for example, in our lungs, there are these specialized structures that you should remember from the first unit called cilia. And these cilia are these hair-like projections at the top of these cells, and they will help trap bacteria and debris. And then they will wave back and forth, creating a sweeping motion, essentially sweeping items out of the throat and nose, which can result in a cough or a sneeze. In your stomach, your digestive system can act as a point of entry for bacteria and other pathogens as well. So the stomach will contain that acid, that hydrochloric acid, that will kill most bacteria should they get to the stomach, or if they do get into the stomach. And that stomach acid is at a pH of 2, which creates fairly acidic conditions. Your eyes can act as a potential entry point as well. So the tears that are secreted by your eyes will also contain enzymes that can help destroy bacteria or other potentially dangerous things. And your eyelashes will also work to keep bacteria out by constantly sweeping over the eye. So when you blink, those eyelashes can help remove debris that gets trapped in the eye. Now, should that pathogen make it past the first line of defense, waiting for them is that second line of defense, which does involve the lymphatic system. So inside the body, the lymphatic system is actually a complex network of organs which work to rid the body of infection. So the lymphatic system is composed of organs such as the spleen, the appendix, the thymus, and the tonsils. And then there are these structures called lymph nodes, in which specialized cells in the body which will help produce those lymphocytes, or is where we find lymphocytes hanging out. So throughout your body, what this diagram shows is where we find a lot of lymph nodes. So there are commonly a lot of lymph nodes around and under your armpit, and then there are lymph nodes just under your throat. So if you've ever been to the doctor and then they ask you to raise your head and they feel under your neck, they're feeling for those lymph nodes to see if they are swollen, because swollen lymph nodes are a sign of an infection. And then sometimes when you're feeling achy from sickness or whatever, and it feels like underneath your arms are really sore, those are the lymph nodes underneath your armpits there that have now become enlarged with reproducing lymphocytes. And then you have lymph nodes found throughout your body. You have a lot of lymph nodes found in your intestinal tract as well, because remember, there's a lot of bacteria that lives in your guts. Now, within that lymphatic system, there is a fluid called lymph. This circulates within the lymphatic vessels, and it's different from blood vessels as it contains white blood cells known as lymphocytes. So the lymphocytes, or those immune cells in your body, have their own vessels in which they can move around the body and they can travel in the blood, as well as these lymphatic vessels as well. So the lymphatic vessels will help transport lymph, which contains those lymphocytes, from organs and tissues to the circulatory system. So it allows them to go back and forth pretty easily. And it allows them to get where they need to go very efficiently as well. So white blood cells, such as lymphocytes, are made in the bone marrow, which is a spongy tissue inside bones. And that's ultimately where those white blood cells will originate from. So the internal defense system begins when white blood cells, known as macrophages, which are our phagocytes, will engulf a pathogen such as bacteria, and that's shown in the picture here. So here we have our macrophage. It's about to engulf this poor little bacteria here. And then macrophages will destroy pathogens with digestive enzymes. So when a macrophage engulfs a bacteria, it does so in a process very similar to endocytosis. So looking at this phagocytosis of the bacterium, if we have our leukocyte, our lymphocyte, or a macrophage, kind of all the same thing, and then we have our bacteria here, the little guy. As the bacteria approaches the lymphocyte or the leukocyte, it will attach to receptor molecules on the plasma membrane of the leukocyte. And this will then trigger the leukocyte then to engulf the bacteria. So this is where the membrane will change shape and fold around it and enclose that bacteria within a vacuole. Once that vacuole has been formed, you'll then have lysosomes, which will then fuse with the vacuole. The lysosomes are filled with hydrolytic enzymes, and when released into the vacuole, will start to break down the bacteria. So once that bacteria is then broken up, the contents of it are dispersed into the cytoplasm. And then the macrophage or the leukocyte will then repeat this process with other bacteria. So should the second line of defense now fail and that pathogen persist despite being phagocytized by macrophages and neutrophils, this is when the third line of defense will start to kick in. And for our purposes, we'll focus in just on antibody formation. So the key cells in the third line of defense are lymphocytes. These are going to be specialized white blood cells, which can be broken down into two categories. You can have a category of cells or type of lymphocyte referred to as B cells, and then a second type of lymphocyte referred to as T cells. So when foreign material enters the body, it will contain a specific antigen on its surface. So antigens can include basically potentially damaging microbes and their toxins, substances such as pollen and flea and dust mite feces. Antigens can include blood cell surface proteins, so proteins on the surface of blood cells, and the surface proteins of transplanted tissues and organs. Basically, an antigen is just going to be a short piece of protein that is going to be recognized by B cells or T cells. And ideally, that antigen that a B cell or T cell will recognize belongs to something like a bacteria or a virus or some other pathogen. So how do B cells and T cells recognize antigens? Well, B cells and T cells have what are called antigen receptors. So on B cells, their antigen receptor looks very much like in the shape of an antibody, and in some ways it's kind of a pre-antibody in a way. T cells have a different type of receptor on them. Both will recognize antigens. So with B cells, with antigens floating in the blood, it will bind to the B cell surface or to the receptor on the B cell. And the antigen has to be a particular shape in order to fit the surface. Not all antigens will fit a receptor. There is only one receptor for one antigen. So in this way, the B cell response will be specific. So B cells can be divided into two cell types. You can have the plasma B cells and the memory B cells. So we'll start with the plasma B cells first. The plasma B cells are the B cells that secrete antibodies into the blood immediately. They begin, once they become activated by that antigen, they begin replicating and secreting antibodies into the blood right away. So those antibodies are proteins that will attach to a specific pathogen antigens. It's a lot to digest there. And so the tip of the antibodies will become specialized for specific antigens. So what does that mean? If we have our antibody here, at the end of the antibody we have an antigen binding site, which is in yellow, and then just note that there's two. Here are the different types of antigens that we could potentially have, let's say from a bacteria. There's only going to be one antigen for this antibody that will be able to bind to its antigen binding sites. The other antigens will not bind to this particular antibody. And so this antibody will be used by the immune system against this particular antigen. Now, there can be other B cells that will produce antibodies that will recognize these other types of antigens, but the B cell producing this type of antibody will only produce antibodies that recognize this one particular antigen. So how does this response all play out ultimately? So if we have our inactive lymphocyte, this is our inactive B cell, it's just kind of hanging around, not doing much, it's just waiting for antigen to show up. So now antigen has shown up, and this antigen is actually specific to the B cell receptor on this particular cell. It'll become activated, and once activated, it will start to divide rapidly. There's only one of this cell right now, and if this is the antibody that needs to be produced, well then there needs to be lots of cells producing these antibodies. So it will start to divide, producing a lot of clones here, and all these clones are all cranking out antibodies that have this same antibody binding site. So these are plasma cells. And then in the end, some of these cells will continue to hang around long term, and these will act as our memory cells, which we'll discuss in a minute. And these are the cells that provide us with long-term immunity to this pathogen. So how do antibodies work? What do they do? So in this case, if our pathogen is a virus, let's say, a virus has some DNA or RNA. It has some type of genetic material. In this case, we'll just assume it's DNA in the middle there, and then on the outside is a protein coat. Now an antibody that recognizes this particular antigen, for example, on this virus, the antibody will bind to that antigen and will prevent this virus now from infecting a cell, and will allow it to be taken up by a macrophage and digested. So as plasma B cells are secreting their antibodies, as those antibodies bind to antigen, it creates what is called an antibody-antigen complex, meaning that you just have antibodies stuck to antigen, and ultimately this will make the microbe easier targets for the phagocytes, such as the macrophages. So there are receptors on the cell membrane of macrophages, for example, that will be able to recognize these antibodies and will make phagocytosis a lot easier for these particular cells. So it will facilitate uptake of this antigen. Antibodies have a number of different roles that they can perform in the body as they help clear out infection. So they can act to neutralize, for example, a virus or a toxin by simply binding to them. It will prevent them from infecting a cell or targeting a cell. Antibodies can cause clumping of antigens as well. So as antibodies start to coat bacteria cells, it can cause them to clump together, making phagocytosis much more efficient and preventing those bacteria cells from infecting surrounding cells. And then it can help precipitate soluble antigens as well, making them less likely to do any damage. And then ultimately all of this works to enhance phagocytosis. So ultimately these antibodies sticking to these antigens causing these different effects is all meant to help enhance phagocytosis and help clear out this infection a lot quicker. So at the end of an infection, When your immune system needs to gear down now and not be in full effect. Some cells, some of these lymphocyte cells, for example, some of these plasma cells will hang around and will stick around a lot longer. And these plasma cells eventually become what are called memory B cells. So memory B cells are long-lived cells bearing receptors for the same specific antigen. So eventually a few cells will give rise to thousands of new cells, as we talked about in that immune response. They're all clones of the original and all specific to that original invading antigens. So memory cells will continue to divide at a low level and will continue to create antibodies for the rest of the life of that organism. So by continuing to secrete those antibodies and continuously producing those antibodies, should that pathogen show up again, the body has secondary response, or that third line of defense, ready to go again to quickly clear out that pathogen. And this is actually how the process of vaccination works. Vaccination allows the creation of memory B cells, and should you ever encounter the actual pathogen, you now have these antibodies present that will help clear out that infection a lot faster. So this is the end of part 1 for 6.3, Defense Against Infectious Disease.